Good afternoon. This is our project presentation on solar panel bike paths. Severe thunderstorms can knock out the power to intersections and their traffic control devices. This can cause delays and accidents. It can take hours, days, and sometimes even weeks for crews to restore power to these intersections. Our solution to this problem was solar panel bike paths. These bike paths can both reduce energy consumption and provide supplementary power to electric car stations, schools, and the streetlights in the area. Backup power would be accessible during severe storm events.
So we looked into Grosjean, Netherlands case study and how they implemented paver solar panel paths for walking around the area, since Netherlands is a big country that is bike heavy. And we took that into consideration when looking at our study and took that towards Atlanta. And based off that, we picked a sunny area south of Piedmont Park on 10th Street near Midtown High School. And in the circles are the two intersections we're going to power. And the length of the solar panel bike path is 1,190 feet, 8 feet wide. And the red box is where the battery power storage will be located. That will hold all the energy that it will be stored in case of a power outage.
And this is a visual reference for what a paver versus panel looks like, and we'll be discussing their pros and cons moving forward. So the paver pros and the panel pros both have recycled materials and high durability, meaning they'll last a long time off of cheaper materials than if they were bought brand new. Whereas the pavers have a more aesthetic integration with their rectangular shape, but the panels have a higher efficiency. Some of the cons would be that the pavers have a less efficient energy output than panels do, but they both have a very high initial cost. So it'll take us a little bit to see the actual fruits of labor for their energy output, with the pavers having a high maintenance cost and the panels having LED built-in lights that could serve as a distraction to residents in the area since they'd be a new addition.
For our study, we picked pavers, and of the area, we get 9,520 square foot of usable area. And these pavers that we picked were 3 feet by 3 feet with half a foot on each side, and with a total solar area of 3,713 square feet, which gives us a total of 1,066 pavers. We did an analysis of the power usage needed, and we found that a total in a single intersection uses 2,800 kilowatt hours per year. And in Georgia, we get 4 hours of peak sunlight, which are the pavers that we have will produce 12 watts per square foot, which produces 65,000 kilowatt hours per year, and that can power 23 intersections. We did a cost analysis as well and found that electricity costs 16 cents per kilowatt hour in Atlanta, Georgia, and a cost of an intersection to run it is $450 per year. To install these pavers, it would cost $200 each, or $213,000 in total. This will eventually will save the city $10,000 per year, and in 20 years, they will make a profit off of the project.
In conclusion, the solar panels and pavers would save us money in the long term and give us a higher quality with the solar pavers that would produce more clean energy that could be used in storm events while generating power into the grid and surrounding utilities and saving on energy costs and work towards cleaner cities. And here are our references for our future reference.